Start recording. Present. Okay, so this is the human reaction time physics project by Daniel Hawkins, Francisco Calderon, and me, Eric Yu. So the reaction strip. The first step is to take the large cardboard and measure out 3 rectangles, all in different sizes, one being 12.7 centimeters by 100 centimeters, the other being 12.7 centimeters by 105 centimeters, and lastly 12.7 centimeters by 110 centimeters. The next step is to fold the 3 pieces lengthwise and form a triangle with one uneven side. And we have 3 different lengths or dimensions because when we're making the reaction time strip, we will be dropping them. We would be dropping the stick at 3 different displacements. So the reaction time strip. As we completed the triangle, we printed out the data that we got through our equations and taped them to a 3.8 centimeter by 100 centimeter length of cardboard. And the equations we use for this reaction time strip are the first equation being this kinematic equation number 2, the second equation being kinematic equation number 1, and the third equation being kinematic equation number 3, and we use these in the order of what is shown. So using the kinematic equation number 2 to find this time for the first reaction time strip, we put the equation in terms of t. To do so, initial Vx naught equals 0 meters per second and delta x equals 1 meter. A sub x equaling 9.8 meters per second squared. Our final equation was t equals the square root of delta x times 2 over a sub x. Then we multiply t by 1000 to get the answer in milliseconds. So equations. For the second reaction time strip, we used kinematic equation number 2 and kinematic equation number 1. We used kinematic equation number 3 and kinematic equation number 1. We use kinematic equation number 3 first to find the v of x of 50 millimeters. In this case, the Vx naught equals 0 meters per second, a sub x equaling 9.8 meters per second squared, and delta x equaling 50 millimeters. We use kinematic equation number 3 once again, but this time Vx naught equals Vx of 50 millimeters, a sub x equaling 9.8 meters per second squared, and delta x equaling 1050 millimeters subtracted by 50 millimeters. Our final equation was v sub x equaling the square root of Vx naught squared plus 2 times a sub x multiplied by the delta x. Then putting in our acquired values from the previous calculations into v sub x equaling Vx naught plus a sub x multiplied by t, we found t, which we then multiplied by 1000 to get ms. For the third reaction time strip, we use v sub x squared equaling Vx naught squared plus 2 times a sub x delta x and v sub x equaling Vx naught plus a sub x t multiplied by t, which is the third kinematic equation and the first kinematic equation again. We need the third kinematic equation first to find Vx of 100 millimeters. In this case, the Vx naught equals 0 meters per second, a sub x equaling 9.8 meters per second squared, and delta x equaling 100 millimeters. we use Vx squared equaling Vx naught squared plus 2 times a sub x delta multiplied by delta x once again, but this time Vx naught equals V sub x of 100 millimeters, a sub x equaling 9.8 meters per second squared, and delta x equaling 1100 millimeters subtracting 100 millimeters. And our final equation was V sub x equals the square root of Vx naught squared plus 2 times a sub x multiplied by the delta x. Then, putting in our acquired values from the previous calculations into V sub x equaling Vx naught plus a sub x multiplied by t, we found t, which we then multiplied by 1000 to get ms. And as you can see from the data, here is the data between our right and left hand. And as you can see that there are 3 displacements being of 0 millimeters, 50 millimeters, and 100 millimeters. Okay. So with 3 people and 3 displacements, and within these displacements there are 10 trials. We have 60 trials for each person, 10 at each different displacement, and 30 for each hand. Here is the mean and standard deviation. And as you can see, for example, at the left hand, person 1 has a standard deviation of 32.72 millimeters and an average of 201.9 millimeters. At 50 millimeters, there's a standard deviation of 26.66 millimeters, an average of 145.6. At 100 millimeters, there's a standard deviation of 88.53 and an average of 223.6. And then looking at the accuracy of the right hand, from our data, people using their right hand tend to have the most accuracy when you drop the stick from 50 millimeters. And you can see that as 12.39% from person 1, 10% from person 2, and 14.54% from person 3 are all the lowest percentages. Looking from the left hand, although it's roughly, there's like a small percentage difference. Out of all 3 subjects combined, when we drop the strip from 50 millimeters, there's much less deviation, and the average of the average, or people tend to, our subjects tend to have a better accuracy at catching at 50 millimeters with their left hand. The pros and cons. So the conclusion, the pros and cons between creating a reaction time strip to measure reaction time is that recording by hand can be unreliable with the error of either over measuring due to the size of their hands, as for example, when they catch it, depending on the size of their hand, it's hard to pinpoint where exactly did they catch it. But having a reaction time strip measurer allows you not to rely on a time watch, which would cause the recorder to react to the person reacting to the stick, which allows more error. So from just this example, a reaction time strip would not factor one more issue as it would if we had a time watch. And this is our presentation. and thank you for listening.